Hey everyone, and welcome to this explainer. Today, we're going on a seriously fascinating journey to demystify the whole concept of optimization. I mean, we all want to make the best choices, right? But how do we actually mathematically prove that a choice is the absolute best? Well, we're going to find out by exploring the foundational concepts laid out in the textbook Stochastic Process Optimization using Aspen Plus. We'll be breaking down the core principles of process optimization and translating some pretty heavy mathematical concepts into clear visual frameworks. Okay, let's quickly map out our path for today. We're going to cover what is optimization, 2, the math behind the model, 3, classifying optimization problems, 4, defining the objective function, 5, working with constraints, and finally, 6, tackling multiple objectives. Let's dive right in. Section 1, what is optimization? It all starts with everyday decision-making. So, how do you choose the best option when making a decision? Think about your morning routine for a second. You choose the fastest route to work, maybe the perfect blend of coffee, or even just the best time to wake up. We literally all make decisions and optimize constantly, often completely unconsciously, just to find the best possible outcome. But while humans kind of just rely on intuition and trial and error, engineering and science, yeah, they require a much more rigorous approach. Because relying on trial and error in, say, a chemical plant, well, that isn't just expensive, it can be incredibly dangerous. And that brings us to our formal definition. Optimization is simply selecting the best alternative among a set of possibilities. It sounds super modern, but humans have actually been doing this systematically for a really long time. The source text notes that one of the earliest recorded optimization problems dates all the way back to Queen Dido around 1000 BC with the isoperimetric problem. Of course, today the scale has completely exploded. We aren't just optimizing simple shapes anymore, we're optimizing massive, incredibly complex systems, like configuring polymer molecules or designing entire continent-wide supply chains for biofuel production. Section 2, the math behind the model. This is where we replace that human intuition with rigorous engineering. To optimize anything using math, you absolutely need a model, an abstract representation of your system using equations. And the very first link between that mathematical model and actual optimization is this deceptively simple formula, F equals N minus M. Here, F represents the degrees of freedom. N is the number of variables in your system, and M is the number of independent equations. Basically, the degrees of freedom tell you exactly how many variables you actually get to freely choose or manipulate. Depending on how that formula shakes out, you're going to land in one of 3 scenarios. Case I is when F is less than 0. You've got more equations than variables. This usually means the problem is overspecified, or, let's be real, there's probably just an error in your model. Case 2 is when F equals exactly 0. The number of equations perfectly matches the variables. This gives you a unique solution. Meaning there are 0 choices to make, the math just spits out the one specific answer. But case 3 is where the magic happens. When F is greater than 0, you have extra variables that you get to choose. So the absolutely crucial point here is that case 3 is exactly where optimization mathematically lives. You have a whole set of possible solutions, and your job is to find the best one. Let's look at example 1.1 straight from the text to see how this can be a little bit sneaky. Imagine a system with 5 equations and 5 variables. At first glance, n is 5, m is 5. 5 minus 5 is 0. You might immediately think, boom, case 2, no optimization possible. But wait a second. If you look really closely at the math, you might find that one equation is literally just the sum of 2 others. It isn't providing any net new information at all. It's dependent. When you remove that dependent equation, your true number of independent equations, your m, is actually 4. 5 minus 4 equals 1. Suddenly, you have 1 degree of freedom. Your seemingly rigid system can actually be optimized. Section 3, classifying optimization problems. Let's break down the different types. Now, what's really interesting here is how the optimization world is essentially split right down the middle based on mathematical relationships. Just look at the top versus the bottom. If your model uses differential or even integro-differential equations, which usually deal with dynamic systems changing over time, you're operating in the realm of optimal control. If you're using standard algebraic equations, you're doing mathematical programming. But definitely notice that secondary split there, uncertainties. If you introduce any uncertainty or randomness into your model, it becomes stochastic. If there are no uncertainties, it remains deterministic or classical. And we can drill down even further based on the exact types of variables and constraints we're using. Honestly, if you've ever heard engineers throwing around this crazy alphabet soup, this breakdown completely explains why. If your variables are continuous, like, say, measuring temperature or pressure, and your constraints are linear, you have LP, or linear programming. If the constraints are nonlinear, you get NLP, nonlinear programming. If you start mixing continuous variables with integer variables, like counting discrete pieces of equipment, you get mixed integer linear programming, MILP, or the highly complex MINLP for the nonlinear versions. Knowing exactly where your problem lives on this chart completely dictates the software and the algorithms you're going to need to actually solve it. Section 4, defining the objective function. How do we actually measure what's best? Remember earlier how we said best is kind of subjective? I mean, to a business owner, best probably means the cheapest. To an environmental engineer, best might mean the lowest possible emissions. To optimize mathematically, we have to totally eliminate that human subjectivity. We do this by defining the objective function. As the source text defines it, it's a numeric criterion. It's basically this completely impartial measuring stick that clearly dictates whether a given solution is better than another. And this brilliantly illustrates what happens when we map that objective function out. On the left, we've got a super simple one-variable objective function. It just looks like a smooth valley. Finding the optimal solution, the absolute lowest point, or global minimum, is pretty incredibly easy here. But look over at the right side. When you add just one more variable, the objective function becomes this wild 3D landscape with all these hills and valleys. Here, you start encountering local minimums. These are little dips that totally look like the bottom if you're just standing in them, but they aren't the absolute lowest point on the whole map. Really complex algorithms are required here to ensure you don't get trapped in a local minimum and that you actually find the true global minimum. Section 5, working with constraints. This is where we face the limits of reality. In most practical problems, our variables aren't just unbounded. You literally can't have negative mass, right? And a physical pipe can only handle so much pressure before it bursts. These very real boundaries create what is called the feasible region. It's the physical, economic, or chemical space where a solution is actually allowed to exist. If a mathematical solution falls outside of this region, it is completely useless to us in the real world. The feasible region is built entirely by constraints, and they generally come in two flavors. First, you've got equality constraints, mathematically written as h of x equals 0. These are incredibly strict. Your solution must land exactly on this line or value, no exceptions. Second, we have inequality constraints, written as g of x is less than or equal to 0. These are a lot more like boundary fences. As long as you're playing inside the fence, the constraint is satisfied. When you are right up against that fence, the constraint is considered active. When you are safely inside the boundary, it's inactive. So the absolutely crucial point here is visually super obvious when you look at these constrained objective functions. Look at how those straight lines and flat planes slice right through the curves of our objective functions. Those planes represent our constraints. They literally chop off parts of our map. And what this means is that the absolute lowest point, that unconstrained global minimum we saw earlier, might now be located totally outside the allowed area. The new best answer is simply the lowest point that also manages to remain inside the feasible region. Sometimes the mathematically perfect answer is just totally illegal in reality, and the constraints force us to settle for the best feasible answer instead. Section 6, tackling multiple objectives. How do we navigate competing goals? Up to this point, we've just had one single objective function to worry about. But what if you want to maximize profit and minimize environmental impact at the exact same time? Welcome to multi-objective optimization. Now you have multiple objective functions, multiple z functions, but they all have to share the exact same physical feasible region. Because these goals almost always compete with each other, improving one usually hurts the other. So instead of looking for a single perfect answer, engineers have to look for a set of what we call non-dominated solutions. It's this critical balancing act. A solution is non-dominated if you cannot possibly improve one objective without making another one worse. And that leaves us with a pretty profound final thought for this explainer. When your objectives are mathematically at war with each other, all trapped within the exact same physical constraints, optimization is no longer just about finding a single bottom of a valley. It becomes this rigorously calculated compromise. How do engineers actually map out these non-dominated solutions to make the final critical decision? Well, that mathematical turf war is exactly where advanced stochastic algorithms truly shine, and it's a completely fascinating area to explore further. Thanks so much for joining me on this structured journey through optimization.